Okay, let's start. Number 10. The Assyrian Siege Machine. Carved into alabaster slabs that once lined a throne room in northern Iraq and now sit inside the British Museum in London, is the most detailed technical record of siege warfare to survive from the entire ancient Near East, cut by sculptors who worked for a king determined to make sure no one would forget what his engineers were capable of building. Ancient Assyrian sources describe these machines in triumphant terms, the war reports of kings recording city after city stripped of its walls in a matter of days rather than months a siege by starvation would ordinarily require. Assyrian royal inscriptions describe the ram as an instrument of terror in its own right, something that broke the will of a garrison before it ever broke the stone, and reliefs from the reign of Ashurnasirpal II, ruling from 883 to 859 BCE, show enemy defenders lowering iron chains from their battlements in a desperate attempt to snag the ram's beam and drag it off target, a detail so specific that it reads less like a royal propaganda and more like an eyewitness account of a specific engineering countermeasure that actually worked, at least sometimes. The physical evidence for these machines is unusually rich for an object built almost entirely from wood, which rarely survives 3,000 years underground. Panel 18 from Ashurnasirpal's Northwest Palace at Nimrod, excavated and shipped to the British Museum in 1849, shows a wheeled siege tower with an armored housing protecting the ram's operators, archers positioned above them shooting down at defenders on the wall, and a separate, freestanding assault tower from which Assyrian bowmen fired directly into the city on level terms with its defenders. A single century and a half later, reliefs from the palace of Sennacherib at Nineveh depict the siege of Lachish in southern Judah in 701 BCE with even greater precision. Earthen assault ramps built up against the city's fortifications, multiple ram towers advancing simultaneously up those ramps, and crews using water hoses to douse burning missiles thrown down by defenders, protecting the leather-covered wooden frames from the one weapon that could reliably stop them. This single siege is documented independently in the Hebrew Bible, in the second book of Kings, and in Sennacherib's own royal annals, making it one of the most thoroughly cross-verified military events anywhere in the ancient world, an event where a stone relief, a royal inscription, and a separate religious text all describe the same machines doing the same work in the same year. Sennacherib's own inscriptions boast that he took 46 of Judah's fortified cities during this same campaign, and the Lachish relief sequence alone runs across more than a dozen carved panels inside the British Museum, following the assault from the first ramp being built to prisoners being led away and impaled outside the captured city, a single continuous visual record of one siege no other ancient civilization left behind in comparable detail. What makes the Assyrian siege engine unusual for its era is not any single technical innovation, since battering rams existed in earlier Near Eastern warfare in simpler forms, but the degree of systems integration on display. This was not one tool, but a coordinated platform, armor plating to protect the crew, a firefighting system to counter incendiary defense, archery support built into the same wheeled structure, and standardized construction repeated across multiple sieges and multiple kings over roughly 2 centuries, from Ashurnasirpal II through Sennacherib to his grandson Ashurbanipal. A besieging army in most of the ancient world before this point had 2 basic options: starve a city out over months, or storm its walls at appalling human cost. Assyrian engineers built a machine that let disciplined infantry cross that gap in days, backed by a logistics chain capable of hauling multi-ton wooden structure across hundreds of miles of Mesopotamian and Levantine terrain to wherever the king's campaign required them next. An empire that built these machines used them as a matter of state policy, tying the deployment of Ashurnasirpal's or Sennacherib's siege towers directly to Assyria's reputation of overwhelming force, a reputation the kings themselves cultivated deliberately in inscriptions, boasting that cities that resisted were destroyed, while cities that surrendered without a fight were merely taxed. The machine and the propaganda were built to work together, each reinforcing the other, so that by the time Sennacherib's forces arrived at a city's gates, the siege engine's reputation had frequently already done half its job before a single ram struck a single wall. 1,000 years after Sennacherib's engineers rolled their towers up the ramps at Lachish, a different set of engineers on the other side of the ancient world solved the same basic problem, breaching a fortified position from a distance using an entirely different mechanism, a bow small enough to be carried and aimed by a single soldier. Number 9. The Chinese repeating crossbow. Inside a 4th century BCE tomb in Jingjiazui in China's Hubei province, archaeologists in the 20th century recovered a wooden crossbow stock fitted with a sliding magazine mechanism that let a single soldier fire, reload, and fire again without lowering the weapon from a ready position, a feature no Western firearm would achieve for another 2,200 years. Chinese military tradition, recorded centuries after the fact in the Eastern Han text Wu Ye Chun Chu, attributes the weapon's invention to a craftsman referred to only as Mr. Qin from the state of Chu during the Warring States period, when constant warfare between rival Chinese kingdoms rewarded any technology that let fewer trained soldiers do the work of many. A far more famous legend, popularized more than 1,000 years later by the historical novel Romance of the Three Kingdoms, credits the weapon entirely to the Three Kingdoms-era strategist Zhuge Liang, who lived from 181 to 234 CE, and the weapon still carries his name today across most of the world, called the Zhuge Nu. The archaeological record contradicts the popular legend directly and by a wide margin. The Jingjiazui tomb, designated Tomb 47, has been dated by Chinese archaeologists to the 4th century BCE, roughly 600 years before Zhuge Liang was born, confirming the textual claim in Wu Ye Chunqiu rather than the version that made it into popular fiction. Separate finds, including bronze crossbow trigger mechanisms recovered from tombs 3 and 12 at Khufu in Shandong province, dated to the 6th century BCE, show that precision bronze trigger technology in China predates even the repeating mechanism by roughly 2 centuries, meaning the culture that eventually built the magazine-fed repeating crossbow had already been refining crossbow trigger engineering for hundreds of years before combining it with an automatic reloading system. The mechanism itself explains why the legend stuck to a real historical figure rather than fading into anonymity. Operating the weapon required only a single forward and back motion of a lever, which simultaneously lowered a fresh bolt from an overhead magazine into the firing channel, drew the bowstring back against the trigger, and locked it in place ready for the next pull. Surviving specimens held magazines carrying up to 10 to 20 bolts, allowing a single soldier to fire that many shots in the time it took a conventional bow user to draw, aim, and release once. Modern historians studying the weapon note the trade-off built into the speed. Draw weights on the repeating crossbow were dramatically lower than on a standard military crossbow of the same period, since the mechanism could not accommodate the full pull strength a soldier's arms alone could generate, and Chinese military writers accordingly recommended coating the ammunition in poison to compensate for reduced penetrating power, a detail preserved in period technical manuals on the weapon's proper battlefield use. The trade-off explains something important about how militaries actually chose which advanced technology to adopt at scale and where. Han Dynasty crossbowmen, whose massed volley tactics historians credit with major victories against Xiongnu cavalry on China's northern frontier, relied overwhelmingly on standard single-shot high-powered crossbows rather than the repeating design, because raw stopping power against a charging horseman mattered more on that battlefield than rate of fire. A standard military crossbow of the period could reach a maximum range well beyond 100 meters, while the repeating design, according to modern historians who have tested faithful reconstructions, typically maxed out closer to 60 meters of effective range, a real and measurable cost for the speed the mechanism bought. The repeating crossbow instead found its most consistent home in a different role entirely:
defensive homes, palace corridors, and city gates, where an attacker was close, lightly armored or unarmored, and volume of fire mattered more than any single bolt's penetrating force. The weapon remained in continuous use in China for well over 2,000 years, with photographic evidence showing it still equipping Chinese troops as late as the First Sino-Japanese War in 1894 and 1895, making it very plausibly the longest continuously deployed firearm equivalent weapon design in human military history. A rapid-fire mechanism built from wood and sinew solved one half of the ancient soldier's problem: speed. On the other side of the Eurasian landmass, different Chinese engineers solved the problem no army had ever fully solved before: how to make 10,000 copies of the same weapon interchangeable enough that any trigger fit any bow.
Number 8. The Qin Standardized Crossbow. Buried alongside more than 8,000 life-size terracotta soldiers in the mausoleum of China's first emperor near modern Xi'an, archaeologists recovered bronze crossbow trigger mechanisms so precisely and consistently manufactured that a team of British and Chinese researchers analyzing them in 2014 concluded they represent the earliest confirmed case of interchangeable mass production of a complex military mechanism anywhere in the archaeological record, more than 2,000 years before Eli Whitney's American armories claimed to invent the concept. Qing dynasty military doctrine, unified under Qin Shi Huang after 221 BCE, treated the crossbow as the backbone of imperial infantry, with formation diagrams recovered from the tomb pits showing ranks of crossbow-armed soldiers positioned to deliver coordinated volley fire, alternating between kneeling and standing ranks so that discharge from the army's crossbows could continue almost without pause, a tactic that assumed every soldier's weapon would perform identically to the one next to it, an assumption that only holds if the parts themselves are genuinely interchangeable rather than individually hand-fitted by a single craftsman to a single stock. Bamboo legal slips recovered from a separate Qin-era tomb at Chuhuidi in Hubei province and translated by scholars in the decades since their 1975 discovery show that Qin state went so far as to write manufacturing tolerances directly into law, with government statutes specifying acceptable variance in the length and weight of standard-issue crossbows, and ordering officials to inspect and penalize workshops whose output fell outside the permitted range, turning what modern archaeologists infer from the artifacts themselves into something that ancient state had already written down as explicit administrative policy. Archaeologist Marcos Martinon Torres, now Pitt Rivers Professor of Archaeological Science at the University of Cambridge, led a team that combined portable X-ray fluorescence spectrometry with detailed metric analysis of 216 surviving bronze crossbow triggers recovered from the tomb complex, publishing the results in the journal Antiquity in 2014. Each trigger was built from 3 separate bronze components, held together by 2 pins, and the team's measurements showed the individual components clustering into a small number of tightly consistent size groups, with coefficients of variation typically below 5% across multiple interacting parts, a level of dimensional consistency that would be difficult to achieve by eye and hand alone, without some form of standardized templates, gauges, or molds shared across workshops. Chinese archaeologist Robin Yates had earlier identified these same crossbow triggers in a 2007 study as very plausibly the first mass-produced interchangeable military artifact in the archaeological record anywhere in the world, a claim the 2014 metric study substantially reinforced. The production system behind this standardization turns out to be more sophisticated than simple assembly line manufacture. Martinon Torres and his colleagues found that the triggers were organized into distinct batches, likely corresponding to output from different workshops or work teams operating under shared specifications, then stored together in a central arsenal before being distributed to specific sectors of the buried army, with the spatial distribution of trigger types across the tomb pits mirroring this batch organization.
A related 2014 study of 40,000 bronze arrowheads recovered from the same complex found comparable standardization in arrow shaft tanks, again organized by measurable batch clusters rather than uniform mass output from one central foundry, suggesting that Qin state had built something closer to a modern regulated supply chain, multiple semi-independent production cells all manufacturing to a shared imperial specification than a single assembly line in the modern industrial sense. What this evidence reveals is a level of centralized industrial organization that historians of technology do not generally associate with any state anywhere in the world until roughly the 18th and 19th century CE, when European and American arms manufacturers began wrestling seriously with the problem of interchangeable parts for muskets and rifles. The Qin state solved a version of the identical problem, coordinating dispersed workshops towards a single tolerances-based specification using nothing but bronze casting, filing, and administrative control over craft labor, roughly 2,100 years earlier, in service of exactly the same military logic that would later drive the Industrial Revolution's arms industry. An army's firepower scales only as far as its logistics can guarantee that any part fits any weapon. Long before any Chinese engineer solved the problem of making one weapon out of interchangeable parts, a Greek engineer working on the other side of the known world had already solved the more basic problem of making a bow small enough and a mechanism simple enough for one soldier to carry it, aim it, and fire it entirely alone.
Number 7. The Gastraphetes. Described in precise technical detail by the 1st century CE engineer Heron of Alexandria in a treatise called Bellopoica, or On Arrow Making, is a weapon its own inventors named for the part of the body used to load it, the Gastraphetes, literally the belly releaser. The device historians consider the direct ancestor of every crossbow built anywhere in the world afterward. Heron's account draws explicitly on an earlier description by the engineer Ctesibius, active in the 3rd century BCE, which places the weapon's actual invention considerably earlier still. The historian Diodorus Siculus records that in 399 BCE, the tyrant Dionysius I of Syracuse assembled a team of the best craftsmen from across the Greek world, offering high wages and rich prizes, specifically to develop new weapons ahead of an anticipated war with Carthage, and traditional scholarship, following the influential 20th century historian E.W. Marsden, credited this workshop with inventing the belly bow. More recent scholarship has complicated that timeline. The ancient author Beton, writing in the 2nd century BCE, attributes an already advanced form of the weapon to an engineer named Zopyros of Tarentum, which would push the actual invention back before 421 BCE, meaning Dionysius's famous engineering workshop likely refined and scaled up an existing weapon, rather than inventing the underlying concept from nothing. The mechanism itself was the genuine innovation, regardless of which engineer receives ultimate credit. Unlike every crossbow that would follow it for the next several centuries, the Gastraphetes was spanned not by pulling the string backward with the arms, but by bracing a concave rest at the rear of the stock against the operator's stomach and pressing forward with the entire body weight, using the torso and legs rather than arm strength alone, to draw a composite bow limb far more powerful than any hand bow a single archer could pull. The bow limb itself was built in layers, a wooden core faced with animal horn on the belly side to resist compression, and backed with sinew to store additional tension. The same lamination principle used in composite bows across the ancient world, adapted here to a fixed stock rather than a bow held loosely in the hand. This let the weapon store meaningfully more energy than a conventional bow, while still remaining something one soldier could carry, aim, and fire without a crew, extending effective range by roughly 50 meters beyond what a contemporary handbow could achieve, according to Heron's own figures, while also letting the shooter take deliberate aim rather than releasing from a fully drawn position under muscular strain. Heron's description is detailed enough, including a technical drawing of the weapon's slider and locking mechanism, that modern historians of ancient technology have been able to build functioning reconstructions directly from the ancient text alone, without needing a surviving physical original, confirming that the mechanism as described genuinely works as a weapon, rather than existing only as an idealized engineering diagram.
Heron explicitly frames the Gastraphetes as the direct conceptual forerunner of the much larger torsion catapult, the katapultikon, that would come to dominate Greek and later Roman siege warfare, describing the belly bow as the small-scale proof of concept that larger stand-mounted machines simply scaled up. What makes the Gastraphetes historically significant is not raw power, which never matched the largest siege engines it inspired, but its role as a genuine category-crossing invention, the first weapon in the historical record designed specifically to let one ordinary soldier, without years of archery training, deliver damage closer to what a much stronger specialist archer could manage, entirely through mechanical advantage built into the weapon itself, rather than skill built into the user. That same underlying idea, mechanical advantage substituting for individual soldierly strength or training, would drive nearly every major weapons innovation that followed it in the ancient Mediterranean world, including a much larger and far stranger Greek machine designed to fire not one bolt at a time, but an entire magazine of them automatically.
Number 6. The Polybolos. Working at the naval arsenal on the island of Rhodes sometime in the 3rd century BCE, the Greek engineer Dionysius of Alexandria built a torsion-powered artillery piece capable of firing bolt after bolt automatically from an internal magazine without requiring its crew to reload between shots. A weapon later Greek engineers themselves nicknamed the Polybolos, meaning simply the multi-thrower. Contemporary Greek engineering culture treated automated repeating fire as one of the great unsolved problems of the age, since existing torsion catapults, however powerful, all required a full manual reloading cycle, drawing the bowstring back by hand or windlass and placing a fresh bolt in the channel between every single shot, a bottleneck that limited even the best trained artillery crew to a fraction of the rate of fire a mechanism without that bottleneck could theoretically achieve. The engineer Philo of Byzantium, active in the same general period as Dionysius, independently encountered and described a very similar machine in his own writings, suggesting the Polybolos or something functionally close to it was recognized across the wider community of Hellenistic military engineers as a genuine solution rather than a curiosity confined to one workshop. The mechanism that made this possible survives in enough technical detail, preserved through the manuscript tradition of ancient artillery treatises, that modern historians of ancient technology have reconstructed its operating principle with confidence. A rotating cylindrical drum, cut with both straight lengthwise grooves and the helical spiral groove running around its circumference, sat above a wooden magazine case loaded with a stack of bolts, holding enough ammunition, based on the dimensions given in the surviving manuscripts, to allow a sustained burst of shots before the operator needed to pause and refill the case by hand. As an operator turned a hand crank connected to the drum through a flat linked chain drive, similar in basic principle to a modern bicycle chain, the drum's spiral groove forced a sliding claw mechanism backward, drawing the torsion-powered bowstring to full draw, while the straight groove simultaneously allowed a single bolt to drop by gravity from the magazine into the firing channel at exactly the right moment in the cycle. Continued rotation released the drawn string, firing the bolt, and the entire sequence then repeated automatically as the crank kept turning, requiring the operator to do nothing more than maintain a steady turning motion rather than perform a full reload cycle by hand between every single shot. Modern historians studying the reconstructed mechanism have concluded the Polybolos could sustain a rate of fire meaningfully faster by a factor of roughly 3 or more than any single-shot torsion catapult of the same power class operated by an equivalent crew, a genuine leap in sustained battlefield firepower achieved entirely through mechanical automation rather than through any improvement in the underlying torsion spring technology that powered the shot itself. The chain drive mechanism at the heart of the design, using a linked chain to convert rotary hand cranking into a precisely timed reload and fire cycle, would not become a familiar engineering principle again in Western technology until medieval and early modern mechanical clockwork, and much later the bicycle and the machine gun, Both rediscovered the same basic chain drive logic independently, more than 2,000 years after Dionysius first built it into a weapon of war. Despite the genuine engineering achievement, and despite Philo's independent corroboration that the concept was real and understood by multiple engineers of the period, there is no surviving battlefield account describing the Polybolos actually deployed in a real battlefield siege or naval engagement anywhere in the ancient historical record. A silence that stands in sharp contrast to weapons like the Assyrian siege ram or Archimedes' engines at Syracuse, both of which show up repeatedly in independent battle narratives written by people who watched them work. That silence does not disprove the machine's existence, since the technical descriptions are too specific and too mechanically coherent to have been invented from nothing. But it does suggest a device that may have remained more prototype than standard-issue weapon. Arguably, the single clearest case among all 10 machines on this list of ancient engineering genuinely running ahead of what the ancient battlefield and its logistics were ready to put to consistent practical use. Automating the reload cycle solved one problem. The Romans, several centuries later, solved an entirely different one, discovering that the wooden frame every artillery piece before them had relied on was itself the weakest and least reliable part of the whole machine. Number 5. The Roman Cheiroballistra. Fragments of an all-metal weapons frame recovered from a Roman military site at Orshova in modern Romania, along with a badly damaged stone-throwing frame excavated at the desert city of Hatra in modern Iraq, together confirmed something historians of ancient technology had suspected for decades from literary sources alone, that the Roman army, at some point in the 1st century CE, completely redesigned its standard field artillery piece around a frame built almost entirely from iron rather than wood. Roman military engineering treated portable field artillery as standard divisional equipment by the early empire, with the writer Vegetius recording that each Roman legion fielded 55 cart-mounted bolt throwers, each one assigned to every century within the legion, each one crewed and operated by a single 8-man squad. Excavations at Masada, the fortress in the Judean desert where Roman legions besieged Jewish rebels between 73 and 74 CE, recovered iron bolt heads and metal fittings consistent with this same generation of Roman artillery, giving historians a second, independent archaeological site, confirming the weapon's real battlefield use outside of Dacia. 5 separate carved scenes on Trajan's column in Rome, commemorating the emperor's campaigns against Dacia in 101 and 102 CE, depict these machines in action on campaign, giving historians a direct, contemporary visual record of exactly what the redesigned weapon looked like in the field. The technical description survives in a manuscript attributed, likely incorrectly, to the 1st century engineer Hieron of Alexandria and known today simply as the Cheiroballistra text, meaning hand catapult. 20th century historian Eric Marsden, in his landmark study of ancient artillery technical treatises, established that this puzzling and long-neglected manuscript was in fact describing exactly the machine shown on Trajan's column, a bolt thrower whose front frame, the section that took the greatest structural stress from the twisted sinew rope springs powering each shot, had been rebuilt entirely from iron, replacing the wooden frames used by every earlier Greek and Roman catapult design, with a distinctive semicircular arched top strut that let the machine's springs be mounted closer together, making the whole weapon considerably more compact without sacrificing power. Historian Alan Wilkins, who spent decades producing full-scale working reconstructions of Roman artillery for academic study and for television documentaries, including productions for the BBC, used Orshova frame fragments alongside the manuscript's precise measurements to build functioning replicas confirming the design could be assembled, tensioned, and fired using only Roman period materials and tools.
The switch from wood to iron solved a problem that limited every earlier torsion catapult design. Wooden frames flexed and warped under the enormous stress of twisted sinew rope springs, gradually losing accuracy and power over repeated use, and were vulnerable to humidity, insect damage, and the simple wear and tear of campaign life in a way that cast and forged iron components were not. An all-metal frame held its dimensions far more precisely shot after shot, meant the machine could be built smaller and lighter for the same power output, which in turn meant it could be mounted on a mule-drawn cart and moved with an advancing legion, rather than left behind as siege-only equipment, and could be more easily disassembled, transported in parts, and reassembled at a new position, exactly the kind of standardized field-portable weapon system a professionalized standing army spread across an empire that stretched from Britain to Syria required if its artillery was going to keep pace with its infantry rather than trailing behind it. A weapon this precisely engineered and this widely distributed across an empire's professional standing army represents a very different kind of ancient technological achievement than a single inventor's singular masterpiece, built once for one city under siege. On the coast of the eastern Mediterranean, a different kind of Hellenistic weapon, cast in solid bronze rather than forged iron, and meant to be used only once in a single decisive collision at sea, would eventually surface from the seabed itself to answer the same fundamental question: exactly how ancient engineers built something meant to destroy an enemy in a single blow.
Number 4. The Athlit Ram. Discovered by chance in 1980 in the shallow waters of Athlit Bay south of Haifa and recovered by researchers and students from the Center for Marine Studies at Haifa University, sits the only fully intact bronze warship ram to survive anywhere from the ancient world, a single continuous bronze casting weighing 465 kilograms, one of the largest single bronze objects ever produced in antiquity. Ancient naval warfare across the Mediterranean depended on the ram as its primary offensive weapon for nearly 1,000 years, a bronze-sheathed timber projecting from a warship's bow at or below the waterline, designed to be driven into an enemy hull at speed and then withdrawn cleanly before the two ships became dangerously entangled, a maneuver requiring split-second timing from a rowing crew and an equally precise piece of engineering at the point of impact itself. Prior to the Athlit discovery, historians' understanding of how these rams were actually built rested almost entirely on written accounts and on stone monuments like Octavian's Victory Memorial at Actium, whose supporting wall is lined with empty sockets that once held captured enemy rams, physical evidence of the objects themselves having been almost completely lost to history. Analysis of the Athlit find has produced an unusually rich body of hard technical data. The ram itself measures roughly 2¼ meters long and stands nearly a meter high, its striking face divided into 3 separate reinforced fins converging into a solid wall at the centerline, a shape engineered specifically to punch through an enemy hull's planking on impact, while still releasing cleanly rather than snagging in the splintered timber. 4 decorative bronze symbols cast directly into the ram, including Poseidon's trident and the star-crowned helmet of the mythical Dioscuri twins, match designs appearing on coins minted in Cyprus between 204 and 164 BCE, allowing researchers to date the object confidently to that window and to associate it plausibly with the Ptolemaic Egyptian fleet under either Ptolemy V or his successor Ptolemy VI. Radiocarbon testing conducted at Israel's Weizmann Institute on wood fragments still lodged inside the ram's hollow casting returned a date consistent with this range. Chemical analysis of the bronze itself using inductively coupled plasma atomic emission spectrometry found a remarkably consistent alloy composition across the object, roughly 90% copper to just under 10% tin, with essentially no lead. A composition matching known Hellenistic bronze statuary standards rather than being some improvised naval-specific formula. A detailed 2006 re-examination published in the Journal of Archaeological Science by researcher Asaf Oran
working through Texas A&M University's Nautical Archaeology program, overturned an earlier theory that the ram had been produced by sand casting, a technique otherwise unknown before the medieval period, concluding instead that ancient founders had used the lost wax method, but had adapted it in an innovative way, casting the entire complex multi-chambered object as a single continuous pour, rather than assembling it from separately cast sections, as most large Hellenistic bronzes were built. What the Athlit Ram demonstrates more clearly than any literary account ever could is the sheer scale of coordinated industrial capacity a Hellenistic naval power needed simply to arm one warship. Producing a single continuous bronze casting of this size and internal complexity required a foundry capable of managing something close to 1,000 kilograms of bronze, poured with enough coordination and speed to fill an intricate three-chambered mold before any section began to cool and solidify unevenly. A logistical and metallurgical challenge on a scale that helps explain why full-size surviving rams are otherwise completely absent from the archaeological record. They were valuable enough as raw bronze alone to be melted down and recast into something else the moment a ship was retired, making the one example that sank, was lost, and was never recovered a genuine accident of survival, rather than evidence that objects like it were common. A single ram, cast once and built to strike once, represents one end of ancient military engineering. At the opposite end sits a Sicilian mathematician's workshop, where the same era's engineering ambition turned towards machines meant not to strike a single decisive blow, but to hold off an entire invading fleet, one grappling hook and one mirror at a time.
Number 3. The Claw of Archimedes. Ancient historian Polybios, writing within roughly 70 years of the events he describes, and drawing by his own account on testimony from people who had lived through the siege itself, records that when a Roman fleet under Marcus Claudius Marcellus attacked the seaward walls of Syracuse in 214 BCE, Archimedes had prepared a device capable of hooking the bow of an approaching warship, lifting it partway out of the water, and either capsizing it outright or dropping it back down with such sudden violence that its crew were thrown into the sea. Roman accounts of the siege, preserved not only by Polybius but also by Livy and by Plutarch in his Life of Marcellus, describe a Roman fleet reduced to genuine dread of Syracuse's defenses, with Plutarch recording that Roman soldiers grew so unnerved by Archimedes' engines that the mere sight of a rope or a length of timber extending over the city wall was enough to send them fleeing, convinced that some new machine of Archimedes' was about to be unleashed against them, a psychological effect Marcellus is said to have found more damaging to his campaign than any single physical loss. Marcellus, according to these accounts, eventually abandoned direct assault entirely and settled into a prolonged blockade, and Syracuse held out for roughly 2 more years before finally falling only through the betrayal of a gate by a defender sympathetic to Rome, rather than through any successful direct assault on its walls. No physical fragment of the claw has ever been recovered, unlike the trigger mechanisms at Chion or the ram at Athlit, leaving its exact mechanical design a matter of informed reconstruction from the ancient texts alone. Roris's own catalog of possible designs, published online alongside his academic work, ranges from a simple pivoting crane arm anchored directly into the city wall to a more elaborate swinging boom mounted on its own turntable, since Polybius's original Greek description is precise about the device's effect on a ship, but frustratingly vague about its exact frame and pivot arrangement. Modern engineers have twice attempted to test its basic plausibility under controlled conditions: the BBC's 1999 documentary series Secrets of the Ancients and the Discovery Channel's Superweapons of the Ancient World in 2005, in which a team of engineers working from the range of possible designs cataloged by Archimedes scholar Chris Roris of Drexel University built a working crane and grapple mechanism within 7 days
and successfully used it to hook, lift, and capsize a full-scale model of a Roman warship. Roris's own detailed technical analysis, co-authored with Harry Harris and presented at a 2001 symposium on extraordinary machines of antiquity held in Olympia, Greece, concluded that Archimedes' documented mathematical work on levers and on the physics of floating bodies gave him precisely the theoretical grounding needed to calculate the leverage requirements such a machine would demand, even though ancient mathematics had no way to perform the kind of precise engineering calculation a modern crane designer would use. What the modern reconstructions establish is plausibility rather than certainty. A working model proves the concept could function as described, not that Archimedes definitely built one exactly this way, or that it performed exactly as Polybius records nearly 7 decades after the fact. But the underlying mathematics is not in dispute. Archimedes had already formally proven the law of the lever and the principle of buoyancy in his surviving written works, the same two physical principles a device like the claw would need to exploit, meaning that whatever the machine's precise construction, the theoretical foundation for building something capable of doing exactly what Polybius and Plutarch describe already existed, worked out and written down, in the besieged city's own library before a single Roman ship ever sailed into range of its walls. A machine built to physically seize an enemy ship out of the water was only one half of Syracuse's reputed arsenal. Ancient and later writers also credited Archimedes with an entirely different kind of weapon, one that used no moving parts and no mechanical force at all, only the sun itself.
Number 2. Archimedes' burning mirrors. Later ancient and medieval writers, including the 12th century Byzantine chronicler John Zanaris, described Archimedes defending Syracuse's harbor with an array of mirrors or polished bronze shields, arranged to focus sunlight onto approaching Roman ships with enough concentrated heat to set their timbers ablaze at a distance, a claim entirely absent from the earlier and more historically reliable accounts of Polybius, Livy, and Plutarch, all of whom describe Archimedes' other engines at Syracuse in detail, but say nothing at all about a heat weapon. That gap in the earliest sources has not stopped repeated modern attempts to test whether the later, more elaborate legend could possibly be true. Greek scientist Ioannis Sakis staged the first serious modern test in 1973 at a naval base outside Athens, arranging 70 sailors, each holding a flat mirror roughly coated in copper, to focus reflected sunlight onto a plywood mock-up of a Roman warship roughly 49 meters away. The wooden target reportedly burst into flame within seconds, though critics later pointed out that the plywood had likely been coated in tar, a substance genuinely common on ancient warships, which ignites far more readily than bare, untreated wood. A more rigorous and widely publicized test followed in October 2005, when engineering students from the Massachusetts Institute of Technology, working with a University of Arizona team and sponsored by the Discovery Channel program Mythbusters, built an array of 127 flat mirror tiles and focused them on a stationary, untreated wooden boat roughly 30 meters away. After approximately 10 minutes of continuous, precisely maintained focus under a cloudless sky, a patch of the hull did begin to smolder and eventually produce open flame, a result MIT professor David Wallace, who led the university's team, described as establishing technical feasibility under close to ideal laboratory conditions, without answering the separate question of whether Archimedes himself actually built and used such a device against a moving target in real combat. Mythbusters itself tested the concept twice on television, in 2004 and again in 2010, using different mirror configurations and different target conditions, and rendered a busted verdict both times. Its producers concluded that a stationary target, a cloudless sky, and roughly 10 minutes of uninterrupted, precise focus made the device wildly impractical as a real weapon against a moving fleet under battle conditions, since ordinary
flaming arrows or bolts shot from a conventional catapult could set a ship alight far more reliably, far more quickly, and from considerably greater range, using nothing more exotic than fire the defenders of Syracuse already possessed in abundance. Even MIT's own final project report on the experiment conceded the same practical point. The ship had to remain still, the weather had to cooperate perfectly, and the beam had to stay locked onto one exact spot for an extended period. Conditions no real naval battle involving oar-driven ships and shifting winds would ever reliably provide. What makes the burning mirror unique among every weapon on this list is that the debate itself is the whole story, rather than an epilogue to a settled question, since the earliest, most historically reliable sources describing the siege of Syracuse say absolutely nothing about it, while later writers, working centuries after Archimedes' death, layered an increasingly elaborate legend on top of a genuinely brilliant mathematician's already well-documented and separately verified reputation for engineering ingenuity. The 6th century engineer Anthemius of Tralles, better known for designing the dome of Hagia Sophia, wrote a separate treatise on burning mirrors that treats the underlying optics as a serious mathematical problem in its own right, evidence that educated engineers across the ancient and early medieval Mediterranean took the theoretical question seriously long before anyone attempted to test it with an actual ship. Modern experiments have proven only that the underlying physics can work, under conditions that bear little resemblance to a real naval engagement, leaving the burning mirror less a confirmed ancient technology than a 2,000-year-old thought experiment in optics that later generations of storytellers and later generations of engineers eager to test them could never quite resist trying to make literally true. Whether or not Archimedes ever truly set a Roman fleet on fire with reflected sunlight, one weapon built roughly 9 centuries after his death did exactly that, using a chemical formula so effective and so carefully guarded that it remains the only entry on this entire list whose core secret has never once been recovered by anyone in any laboratory in over 1,300 years of trying.
Number 1. Greek fire. The Byzantine chronicler Theophanes the Confessor records that in the Byzantine year of 672 CE, an engineer named Kallinikos, a refugee who had fled to Constantinople from Heliopolis in Syria after the region fell to the armies of the early Muslim conquests, arrived with a formula for what Theophanes calls simply sea fire, a liquid weapon that could be projected from Byzantine ships to ignite an enemy fleet and continue burning even on the surface of open water, defeating the one defense every sailor of the age could otherwise rely on absolutely. Byzantine military tradition treated the formula itself as a state secret of the very highest order, guarded, according to later Byzantine sources, as closely as any secret the empire possessed, restricted to a tiny circle of the emperor's most trusted officials, and passed down, according to tradition, only within a single family line for generations, precisely because the empire's leadership understood that the weapon's psychological terror depended entirely on the enemy never being able to reliably reproduce or reliably counter it. The delivery system evolved well beyond its original ship-mounted siphons. By the reign of Emperor Leo VI in the early 10th century, Byzantine forces were also using a smaller, portable hand siphon version of the weapon, closely resembling a modern handheld flamethrower, deployed by infantry against massed enemy formations on land rather than only against ships at sea, according to Leo's own surviving military manual. The Emperor Constantine IV deployed the ship-mounted weapon for devastating effect during the extended Arab siege of Constantinople that began the following year, and Greek fire went on to help preserve the Byzantine capital against repeated existential naval threats for centuries afterward, a single guarded formula functioning for generation after generation as one of the empire's most important strategic assets. The secret succeeded completely. The precise chemical formula for Greek fire has never been recovered, in any language, in any archive, anywhere, and modern chemists and historians remain reduced to informed speculation built from scattered clues in surviving Byzantine texts.
Historian John Haldon, working with engineer Maurice Byrne, published an influential proposed reconstruction of the weapon's delivery mechanism in the German academic journal Byzantinische Zeitschrift in 1977, theorizing a system built around a pressurized bronze tank heated over a brazier, forcing preheated liquid through a swiveling bronze nozzle, the direct historical and mechanical ancestor of the modern handheld flamethrower. Haldon tested this theoretical design physically in 2002 for the television series Machines Time Forgot, and again built a full-scale working version in 2006 using Crimean crude oil mixed with wood resins, a combination consistent with Byzantine access to naphtha deposits around the Black Sea. The full-scale 2006 device achieved a flame temperature exceeding 1,000 degrees Celsius and an effective range of up to 15 meters, and functioned, in Haldon's own account, well enough to confirm the underlying mechanical principle, even while using nothing more than materials and basic techniques genuinely available to 7th century Byzantine craftsmen. Haldon's team did note one telling limitation their reconstruction could not overcome. Modern welding technology still struggled to keep the pressurized bronze tank from becoming dangerously unstable under sustained use, a structural failure mode never once mentioned in any Byzantine account of the weapon actually being operated in the field, suggesting Byzantine engineers had solved a materials or design problem modern reconstruction has still not fully matched. Chemical analysis of the surviving textual clues points towards a mixture built around light petroleum or naphtha, likely sourced from the Crimean region north of the Black Sea, combined with some blend of resin, sulfur, and quicklime, with some later medieval commentators suggesting the mixture may have also incorporated an early form of the same saltpeter compound that would eventually become essential to gunpowder centuries afterward, though no combination proposed by any modern researcher has ever been confirmed as chemically identical to what Byzantine sources actually describe firsthand. The formula's disappearance was not an accident of lost records or a simple failure of documentation, the way so many other ancient technologies fade from history through ordinary neglect. It was the direct and intended result of a system of secrecy so effective, sustained across multiple centuries of imperial administration, that it outlasted the empire that built it, continuing to defeat the tools of modern chemistry and historical reconstruction just as completely as it once defeated the ships of the 7th century Arab fleets it was built to burn.
10 machines spanning nearly 1,500 years and 4 different civilizations, from the Tigris to the Bosphorus, share one underlying trait beneath all their surface differences. Each one solved the problem its own century was not fully equipped to solve through ordinary means, whether that problem was breaching a wall, striking a moving ship, arming 10,000 identical soldiers, or defeating an enemy fleet's only reliable defense against fire. Look at the list a second time, and a quieter pattern emerges alongside the first one. The machines built to solve a single, narrow, well-defined problem, a bolt thrower's frame, a ram's striking face, a crossbow trigger's tolerances, are the ones whose evidence survives cleanly today, recoverable from mud, from tombs, from a Romanian riverbank, because a narrow problem produces a physical object simple enough to leave a durable trace. The machines built around an entire system, a fleet-defeating chemical weapon, a city-terrorizing siege platform, a claim about mirrors that may never have existed at all, survive instead mostly as argument, as competing ancient testimony that modern engineers keep trying and mostly failing to settle definitively, one experiment at a time. Some of these machines left behind bronze and iron that archaeologists could hold in their hands, weigh, date, and test. Others left behind only the fear they caused in the men who faced them, recorded independently by writers who had no reason to agree with each other and every reason to exaggerate, yet whose accounts, checked against the physical evidence that does survive, keep turning out to be more accurate than centuries of later skepticism assumed. The rarest achievement on this list was never the biggest machine or the widest attribution. It was the ability to solve a problem so completely that the solution's secret, unlike the swords and siege towers all around it, actually survived to remain unsolved. If you want to see what happens when a different civilization's lost technology finally gets cracked open by modern science, click the video on screen.